Example 5.14, speedboat power. Problem. What average power would a what is that? I can't even read it. Okay, I think that is a 3. So 1,000 kilogram speedboat need to go from 20 meters per second in 5 seconds. Go from rest to 20 meters per second in 5 seconds, assuming the water exerts a constant drag force of magnitude 500 newtons, and the acceleration is constant. In part B, find an expression for the instantaneous power in terms of the drag force F sub d, the mass m, the acceleration a, and the time t. So we have a mass of 1,000 kilograms accelerating from 0 to 20 at constant acceleration with a drag force of 500 newtons on it. We want to use E initial plus work non-conservative equals energy final. We will have basically 0 energy at the beginning. The work done is going to be the work of the boat plus the work done by friction. And the energy at the final, it's going to be going 20 meters per second. So it'll be 1/2 mv squared, v final squared. Oh, I missed one thing. Delta t was equal to 5.00 seconds. So that's important. So what can we say about this? The work of the boat is what we want to get to divide by 5 seconds, really. So really, first let's find work of the boat. The friction will be minus 500 newtons times the distance. What's the distance? We'll have to calculate that one. Actually, you know what? Let's go ahead and leave it in letter form. The drag force times the distance equals 1/2 mv final squared. And then we will solve that. Delta x could be, how do you want to solve it? With v final and v sub naught? V final plus v sub naught over 2 delta t. That would be the average velocity times the time. That would be one way of solving for the distance. And so work of the boat. Okay, so equals 1/2 mv final squared. So now we've got everything that we need. I'm going to go ahead and add this to both sides. 500 newtons of frictional force. The average velocity of 20 and 0 is 10 meters per second times our 5 seconds, plus 1/2 times our mass of 1,000 times our v final squared. And let's multiply that out. So I got a total work of 225,000 joules. So our power is going to be equal to the work over delta t. So 225,000 divided by our 5 seconds is 45,000 joules per second, equals 45,000 watts, or divide by 746 watts per horsepower, and you get 60.3 horsepower. Now let's take this expression here and not this one, this one. Let's take this expression here and move it over here so we can get power as a function of the drag force, the mass, the acceleration, and the time. And all right, I went down a wrong track but I'm editing that. I was thinking the equation I just used is an equation for average power. Power equals force times average velocity, which in this case just comes out to be uh, force times velocity final over 2. But they want the instantaneous power, which is power equals force times the final velocity. And in order to get that, let's first think in terms of Newton's second law, sum of forces over m, which in this case will be um, the force of the engine minus the drag force, so over m. So ma plus the drag force is equal to the force of the engine, and the velocity will be velocity started at 0, v sub naught plus at, so in this case it will just be at. So the work, or the, okay, so force times velocity, power, instantaneous power will be force times velocity, which will be the force of the engine, ma plus f sub d, times the velocity, which is at. So you notice that this power is increasing linearly with time. Oddly enough, at the very beginning when t equals 0 and the velocity is 0, there's no power coming from the engine. But as it gets faster and faster, there's more and more power coming from the engine, more and more wattage. And they have this remark here that says, in fact, drag forces generally get larger with increasing speed, but even without an increasing drag force, we have an increasing wattage coming out. Question 5.14, how does the instantaneous power at the end of 5 seconds compare to the average power? The instantaneous power is force times velocity. The average power is force times average velocity, so it would be exactly half of the instantaneous power.